Hello, welcome back to the session on your process synchronization, your fourth unit, part one. Okay. So in this particular session, we'll be discussing about the very important topic, or you can say that very famous or most important topic relevant to your process synchronization. That is what we call it as semaphores. So today we will be discussing in our this particular session something called as semaphores. Yes, we will be discussing only one concept in this particular session because it's very important as per your exam point of view and as per your technical point of view. Because technically how this is a because semaphores is the one using which we can apply this particular process synchronization mechanism. So in the previous sessions we discussed about something relevant to what do you mean by process synchronization? In the background, we discussed about something called as process synchronization. So what do you mean by synchronization? So I think you people right now, since we have completed around 2 to 3 different sessions related to process synchronization, you will be very much aware with respect to your concept called as process synchronization. What do you mean by exactly how process synchronization and how we can do that synchronization? And for that, we discussed the very famous problem. What we have is critical section problem. So if any of you have any doubts relevant to it, you please watch my previous sessions. What we have, I have uploaded in the YouTube so that you can get a clear idea with respect to your critical section problem. And to this particular problem, we discussed something called a software-based solution. A software-based solution to your critical section problem, and that is what we call it as Peterson solution. And we also said that it has certain limitations that we cannot apply to the modern computer architectures here, since it can be applied only to the two processes, either P0 or P1, or it can be like P1 and P2, depends. So any two different processes when you are having, then only you can implement this particular Peterson solution. That's the reason we cannot. So to overcome that, we have seen in the previous session something called as hardware related solutions to your critical section problem, where we discussed about something called test and set method, and after that we discussed about something called as compare and swap, I think. Okay, so we discussed something called as compare and swap. So these two methodologies what we have seen in the previous session, and in this we discussed that with the help of this we are able to provide the mutual exclusion, but we were not able to provide something called as bound waiting and progress. So in order to provide this, we just came up with a different algorithm which actually satisfies all the three requirements for your mutual critical section problem. So today's session is mostly or most importantly focused on this particular concept called as semaphores. Yes, actually semaphore basically it's nothing but it's a variable. It's simply a variable. We basically call it as an integer variable. Like in C program, you people might be declaring variables int a comma b comma c. Same way, so this a you can assume it as a semaphore. This b you people can assume it as a semaphore. Same with c. Okay, so this is a very important concept. Using this particular variable, we will be making sure that no two processes are actually entering into the critical section simultaneously. Like till now we have seen problems, something like software-based problem, but this cannot be implemented. But it has given a good theoretical explanation how we can write algorithms. Okay, complex algorithms, how we can write it, that explanation is given beautifully in this particular solution. And coming to the hardware, okay, we will be implementing this. That's fine, not a problem. But this is hardware related solutions. So we need to develop programs. We need to develop programs means it's nothing but it's a software, right? So in order to develop that, definitely we need some mechanism. That's the reason we are implementing this particular semaphore concept. Okay. And then we have something called classical problems and synchronization. This will see in the next session. Followed with that, we will be discussing about monitors. So semaphores and monitors are very important topics. And what are the problems we are going to discuss here in this particular synchronization problems, classical problems, what we have, we will be giving solutions using this monitor. Okay, so this will be in the next session. In today's session, we'll be just focusing on this particular concept called as semaphores. So let's begin the topic here. So what do you mean by semaphore? Well, basically, this just an introduction part what we are giving here. Since he is saying that we already discussed about the synchronization tools, right? That is nothing but he's talking about your mutex law. The previous session we discussed about mutex law. So the operating system designers, they actually developed some software tools I have said. right? So these software tools is nothing but mutex lock. I think you people are familiar. What do you mean by mutex here? So MUT is nothing but a mutual. EX is nothing but exclusion. So mutual exclusion lock is provided, which is having a value of either 0 or 1. So 0 indicates that that particular variable means that particular lock is acquired by some particular process, and 1 indicates that that particular lock is free. Anyone can try to access it. Okay. So whenever the lock, see, there might be a small difference in the previous scenario. I'm saying like I might have interchanged them. 0 represents that that particular lock is already acquired by some process, and 1 indicates that that particular lock is free, means no one has acquired that lock, anyone can try to access it. So 1 represents free and 0 represents lock. So this is a small change that we are going to do in this particular session. So the previous session also when we were discussing, I think there is a small overlapping has been done, that 0 has been indicated locked and 1 indicated as something called as, I mean 1 as a locked and 0 is free. So you please change it up. So 0 represents that there are no locks available. It indicates that the locks are already used by some process. Whereas 1 indicates that that particular lock is free. Anyone can enter into the critical section and perform its stuff. So that is what been represented here in this particular thing. So we have been provided with different synchronization tools. Same way, the since as the technology evolved, more awareness came among this particular technology started developing. So those who had a good ideas for implementation, they started developing their own methodology. So then came a semaphore here. So one of the person has developed a semaphore. Well, basically what do you mean by this S? Means semaphore is generally represented with a variable called S. Okay, it's a non-alphabet used S, and this is an integer variable. Remember that it is an integer variable. So apart from initialization, so after initialization, it can be accessed only with the help of two different operations. Means not every method or every function can use this particular semaphore. It can be accessed only with the help of two different methods, or you can say functions. That functions are wait and another one is signal. Only these two are the operations which can access that semaphore, which can access semaphore is. Okay, apart from that, no one can access that particular semaphore variable. Now, what about this particular functions? What do you mean by this wait and signal? Well, basically, till now you people might have got an awareness related to this critical section problem. How so whenever a process want to enter into the critical section, that particular process should request, okay, to enter into the critical section, and I think that is what we call it as entry section, right? So once he is getting a permission to enter, then he will be executing in the critical section. And once he completes it, he should give acknowledgement to the others that I am leaving this critical section. And I think that is what we call it as exit section. Then we have a reminder section. Fine. I am actually concentrating on these two, entry and exit. So here this entry section is nothing but this terminology has been changed with your wait operation. Yeah. So whenever a particular process want to enter into a critical session, now this time from now onwards, that process will be executing wait operation. And in this wait, if the particular, critical section is available, then that particular critical section will be allocated to that particular process. In case the critical section is busy, then that particular process will be waiting. Okay, that's why we are representing the function with wait. So that particular process will wait until the critical section is free. Okay, and I think you can guess where signal can be used. Yes, of course, you will be using an exit section. So once the process is given a chance to enter into critical section, after performing the operation in the critical section, okay, when it is coming out in the entry section, he will give a signal. Since I am telling you that the process which has completed executing in the critical section, they have to acknowledge the other processes related to that I am leaving this critical section. So that is what I'm calling it as here signal. They are calling, the author is calling it as signal. So using signal with that particular process is giving a intimation to the remaining processes that, okay, I have completed executing in the critical section. If anyone wants, they can come and access this particular critical section. So in next process, whichever is coming to access this particular critical section, the same process has to follow. First, it has to execute a wait operation. If the critical section is free, that will be given to that particular process. If it is not, it has to wait. Same way, once the process completes executing in the critical section, they have to give a signal to the other processes that I have completed executing it. Now you people can come and access the information. So simple technique what we are going to use. So simple way to remember what do you mean by semaphore is nothing but basically it is represented with a variable yes. It is an integer variable that apart from initialization can be accessed only with the help of two different methods, or you can call it as functions, whatever you like, or you can call it as operations. Okay, you can call it as methods or operations or functions. Depends, whatever you would like to say, everything is correct. So what are the operations we do have? Wait operation and signal. Since you can see these are the operations or functions we are representing with the open and curly small brackets. So within this you may be getting parameters. Right now just this is quite sufficient. You don't have to worry about the parameters, what parameters we use. Just remember that we are, okay, just let me revert. So semaphore S is an integer variable, can be accessed with the help of two different operations, wait and signal. Now coming to this particular wait, it actually came from some location called as P. Basically it is called as P. So what do you mean by P is nothing but in Dutch we call it as proheben. Proben, okay? So what do you mean by proben is nothing but to test. So test in the sense, I think you people now get a clear idea. Test and set we used. So something like that. So it is actually a Dutch word. Wait operation has come up, or we usually call it as a P. Okay, and it is a Dutch. In Dutch, we would call that P as proheben, means to testing. So we are testing whether that critical section is free or not. Whenever a process wants to enter into the critical section, it will first test whether this particular critical section is free or not. If it is free, then we will be entering into it. If it is not free, the process will enter into a wait state. Okay, so whichever process you might take. And whereas coming to signal, the signal is called as V. Remember, so wait operation, we are representing with the, the alphabet called P, whereas coming to signal, we are representing that with V. V is nothing but verhogen. Verhogen means to increment. So whenever a particular process is using this particular critical section, this will have instances. Well, we are talking about here with respect to resources. Remember now, this time I'll explain them so that you can get a clear idea. For timing, you remember that whenever a process is trying to access a critical section, that critical section will be decremented. Now this critical section is with respect to the resources. I will explain in the coming slide. So P, what happens whenever a particular process accesses this particular critical section, it will first decrement the value. That is what we call it as test. And whenever he completes performing execution with the critical section, he is coming out of it, he will increment the value so that other process can try to access it. So that is what we call it as signal, and the signal is nothing but we call it as verhogen. The meaning for that is to increment. Okay, so based on that, we have a structure for wait and signal. Now this is the structure what we have, the basic structure what we use it. Now wait of S, I think you people are familiar now with this. S is nothing but your semaphore. Now what is the condition he is using here is that while S is less than equal to 0. Well, this particular variable is either less than or equal to 0, you will be entering into a busy state. Means what did I say? Whenever a process wants to access a critical section, he first executes a wait signal. So whenever the process even try to execute, he will first execute this wait. And in this, he will try to see whether this particular variable value is greater than 0 or not. If it is greater than 0, that is nothing but 1. That indicates that that particular critical section is available. Then it can be allocated. But since if it is less than 0 or equal to 0, means all the particular critical section is been used. So we cannot allocate to it. Then that particular process should enter into a waiting state. That is what we call it as busy waiting. That we have already seen in our previous video with respect to a mutex clock. Mutex clock has some disadvantage. We discussed it. Something we call it as busy waiting. The other name for that is spin lock. So what do you mean by spin lock is a process when it is requesting for a critical section and if it is that is not available, it will wait for some time. Again, it will try to execute that particular wait operation. So again, it will wait. Again, if the critical section is busy, it will wait for some time. Again, it will ask. So it will keep on repeating this process. Okay, and that is what we basically call it as a busy waiting. Now, In this case, in case if that particular critical section is available, simply what we are going to do, this condition fails. So we are simply doing S minus minus. As I told you that this particular critical section is allocated to P1, then P1 will be decrementing it so that no one else can try to access it. So definitely the value of S will be either 1 or 0. Okay, so if it is 1, it indicates that this particular semaphore is available, means a critical section is available, anyone can try to access it. If the value becomes 0, that means that critical section cannot be accessed by any other process because it is already been used, it is busy. So whenever this is available, we will decrement it. Suppose initially S is equal to 1, no one has tried to access it. P1 executed wait operation. So what is the value of S? 1. So 1 is less than equal to 0, condition failed. So what he is doing, we will allocate that critical section to this particular process P1. Then what P1 will do, S minus minus. Now what is the value of S now? 0. Now another process P1 came, he executed W2. But what about the value of S right now? We have 0. So while 0 less than equal to 0, condition satisfied because it is equal to 0, means critical section is not available. So what that process will do, P2, it will enter into a busy state. Until what time? Until P1 is leaving that critical section. Whenever P1 is leaving the critical section, he will call signal. So S plus plus. Then what is the value of S now? It is 1. Now when this process will execute, when the value of S has become 1, when P1 has executed this, now when this particular process P2 has started executing wait, now the value of S is 1. 1 is less than equal to 0, condition failed. So we can allocate P2, this particular semaphore means critical section can be allocated to this particular process. Then again what we will do, S minus minus. Now what is the value of S again? 0. Okay, I hope you got it what I'm saying doing here. So definitely if another process comes, since the value of S is equal to 0, we cannot allocate it. Now this process will be in a busy waiting state. Now once again when the process T2 completes executing, he will be calling S plus plus. So now the value of S becomes 1. Now another process can try to access, maybe P3. So this is the way how your exact program works. Okay, let me explain this one more time so that you can get a clear idea. Let us suppose initially the value of S is 1, means that particular semaphore value is 1 and this is related to your critical section. So whenever S is 1, it indicates that critical section is free. When S is 0, it indicates that critical section is busy. We cannot allocate it. Now we have two processes P1, P2. P1 initially came and he has executed wait. So what is the value of S right now? We have 1. So 1 is less than equal to 0. Condition failed. So he doesn't have to enter into waiting state. Why? Because the semaphore is available. Semaphore is available means that indicates that critical section is free. So what we are going to do, we'll execute this step, S minus minus. So what is the value of S we are going to have here? 0 and P1 is allocated the critical section. Now P1 here, in this case, where it is, yeah. So in this case, P1 is having this particular critical section. Now immediately after that P2 came. P2 also executed. Now P2 has executed waiting state. Now what is the value of S we have right now? 0. Now while 0 is less than or equal to 0, condition true. That indicates that critical section is not available. Now what the P2 has to do? He should enter into a waiting state. You're getting my point? So this particular process will enter, P2 will enter into a waiting state. Now he will wait for some time. Again he will execute wait. Again he will find that semaphore is value is 0, so he will enter into waiting state. Keep on rotating like that until what time? The P1 is releasing that critical section. Now P1 has completed executing in the critical section. He is coming out. So exit section he is calling signal S. So what happened here? S plus plus means nothing but the value of S becomes 1. Now he came out. This particular process completed execution. P2 is trying now. This time again he is executing now. Now this time the value of S is 1. Now 1 is less than equal to 0, condition failed. Skip this particular part. So S minus minus, now S becomes 0 and the critical section is allocated to process P2. Now P2 is executing in critical section. And once P2 completes execution, he will call signal. Now again the S value will become 1. So this is the whole process how one by one the processes are going to enter into the critical section and execute the entire process. I hope it's very clear with this. Okay. Now in this we are going to discuss about usage here. Well, basically here I will explain you why that less than equal to 0 concept and all is coming up. So here the semaphores are basically classified into two types. Okay, so we have something called as counting semaphores, and then we have something called as binary semaphores. So what about binary? I think you people are familiar with this. So we have only two values here, 0 and 1. And this is what I can say. We can implement this like something mutex lock. In the previous session, we discussed about mutex lock. Same thing is concept as this binary semaphore. This is used whenever we are allocating a critical section problem. But whereas coming to counting semaphore here, this is somewhat different. Here we will be having numerical numbers 1, 2, 3, and we have unrestricted domain for this, like something like n, unlimited. And this counting semaphore, okay, so this is what we call counting semaphore here. So 1, 2, 3, so on up to n. These many semaphores we can represent using counting and binary. Okay, now the first thing that comes in mind is which one to use where. So basically this binary semaphore we will be using whenever we are allocating a critical section to a process. So 0, I told you, 0 indicates that no critical section is available. No critical section is available. It indicates that all are busy. All the critical sections are busy. And whenever you're representing 1, that indicates that critical section is free. And any process can try to access that particular critical section. But my major concentration on this particular counting here. So if you talk about your counting, we have 1, 2, 3, so on. So we have an unrestricted. We are using it as unrestricted domain here. So what do you mean by unrestricted means there is no limit. It is infinite. 1, 2, 3, so on up to n. And where we are going to use this counting semaphore means this we are going to use it in your concept something called as resources. Well, we discussed it that every resource will have some instances. I don't know how many of you remember this. Every resource will have some instance, right? For example, if you take a printer, if I'm taking a printer, at a time, 10 people can give command to the printer to print it. Okay, obviously the output will be coming one after another. Means what we are saying, this printer will have a queue, right? This printer will have a queue of size 10. So 10 people simultaneously giving a print, so that will be queued here. So this is like process 1, process 2, process 3, process, means user 1, 2, 3. So one by one the printer will exist. This is what I'm talking about instances. So every resource, whatever you're seeing here or you might be using it, it will have some set of instances. Okay, like for example, if you take a Wi-Fi router, okay, if you're taking a Wi-Fi router, the maximum limit that, for example, assume that 10 people can at a time simultaneously access this particular Wi-Fi router. What does that mean? This is a resource, and this resource having 10 instances. This particular resource is, I mean, 10 people can simultaneously access that particular Wi-Fi resource. But if the 11th person is coming, he has to wait until one of the person is leaving. Among the 10 people, one of the person is leaving that resource, then only the 11th person can get a chance to be a part of this particular router. So that is what we call it as instances. Now this particular counting semaphore, we actually use it for resources. Okay, so based on that, we will determine that how many resources this particular resource can be allocated to how many processes and how many instances are left. Okay, and can we allocate? If another new request is coming from a process for this resource, do we have an instance of this resource or not to be allocated to that particular process? That we can determine using this particular concept. Okay, so let me give you a practical view of it so that you can get a clear idea with respect to this. Since I told you, we have a counting semaphore, okay, and then we have a binary semaphore. So binary semaphore is similar to a mutex block. That is what I have explained it. Now here, well, before going to talk about this particular synchronization problem, I just want to spend some time with respect to your counting semaphore here and your wait operation. Now this counting semaphore with respect to your wait and signal. Because in this we have something s less than equal to 0, here s plus plus. So that I want to explain with respect to your counting semaphore. Now every process, as I told you, this counting semaphore, we can use it with respect to your resources. So anytime, whenever a process want to access a particular resource, okay, use a resource. First, the process will execute a wait operation. It will execute a wait operation on that semaphore. So whenever the process releases, so whenever a process completes execution and release that particular resource, it will be calling a signal operation. So whenever the count of that particular semaphore will be zero, whenever the count of that particular semaphore becomes zero, that is in the wait, if the S becomes zero, that indicates that all the resources are being used. That's the reason we have used S less than equal to zero in wait operation, isn't it? Okay, let me write it up. So wait of S. So while S is less than equal to zero, so what we are doing? Busy waiting. Else S minus minus. What we are doing exactly here, S less than equal to 0 indicates that all the resources of means all the instances of that particular resource are already used by this particular some other processes. So we don't have another resource, instance of a resource to be allocated to that process whichever is requesting. So that particular process should enter into a waiting state. And in case if the resource is available, we'll be performing S minus minus, and that instance of a resource can be allocated to that particular process. And what about signal then? Same. So whenever a process completes executing, like I told you in the printer, we have 5 instances, let us suppose. So user 1, 2, 3, 4, 5. So whenever 6th user is coming, he is requesting, but this is full. So that's why we are not doing it. So here, that's what we are seeing here. So since it is full, so what does that mean? S value is equal to 0. So it has to wait. So it is waiting. The 6th process or the 6th user is waiting one of them to complete. So whenever, let us suppose the one has completed executing, now this becomes 2, 3, 4, 5. Now this is an empty slot here. Now we can allocate here 6. So how we are allocating means whenever one completes, he will give a signal. So in signal, what happens? The value of S becomes 1. So there is a availability. Then 6 will be given to this. Now again the S value becomes 0. Now if the 7th process is coming up now, he has to wait. Why? Because right now the queue is something like 2, 3, 4, 5, 6. The 7th process has to wait because the value of S is 0. Now when 2 completes executing it, he will signal. So when he is giving signal, the value of S becomes 1. Now whenever he is executing a wait now, he'll come to know S value is 1. So definitely he can be allocated it. So now what are the Q value will be here? 3, 4, 5, 6. So 7, since the value of S is 1, 7 can be allocated. Now 7 will make S minus minus. That is S value becomes again 0. So this is the way how it exactly works. So the counting semaphores are mostly used for what? We are going to use is nothing but your resources, the instances of resources. And this way it is going to actually perform the operation. Okay. So let's take a small example. Okay, so basically we can use this particular semaphores also for solving the synchronization problem. That is what he's saying here, and I am going to explain that with the help of a small example so that you can see here. Let us suppose that we have two different processes here. First we have a process P1 and another process I am taking P2. And in the P1, so in the P1 you are having a statement S1 and in the P2 you are having a statement S2. Okay, means this process is generated, this process is created to execute a statement S1 and this process is created to execute a statement S2. Now, there is a condition here. There is a condition. What is the condition? That S2 can execute only when S1 completes. S1 should complete, then only S2 can execute it. That is the condition I am going to place it up. Okay. See here. What is the condition is S2 can be executed only after S1 has completed. Means the process P1 should complete the execution first, then only P2 should be given the chance to execute it. Now, how we can do it? So what we are going to do here in this particular case, for this particular P1 and P2, I am going to use a common variable semaphore, SYNCH. This is a semaphore I am using. And I think you people know what do you mean by semaphore? It is the integer variable. I am simply taking a variable. In programmatic point of view, this is nothing but a variable we are using in a common programming. C program, how we use it variables. So think I am using a common variable for process P1 and P2. Now, in this case, what I'm going to do is, using this particular semaphore, I will write the statement. So let's see the statement. This is a statement for P1 and this is a statement for P2. Let's see whether it is satisfying this particular condition or not. Let's see. So P1, it is executing. So P1 is executing S1, then P1 is giving signal. Okay. Whereas coming to P2, it want to enter into the critical section, so it is calling the wait operation. Wait with sync. You can see both are common variables, what we are using, then S2. Now what will happen here? So initially, the value of sync is 0. Why? Because already P1 is allocated that critical section. So P1 is executing now this particular statement. So what will be the value of this particular semaphore? 0. So that's why he's saying 0. Now when it is executing, P1 is executing S1, P2 wanted to execute, so he called wait operation with semaphore sync. So what is the value of semaphore we have here sync? 0. Now I think you know the condition. While sync is less than equal to 0, what do you have to do? Is the waiting. Else S minus minus. So since the value of 0, so 0 less than equal to 0, condition satisfied means someone is already using the critical section. Then what the process P2 has to do? Simply he has to wait. Until what time? Calling signal. So the P1 is calling signal. You know what is the command we have in signal? So that is S plus plus. Now the S values initially. So here we are using a synchronized variable. So SYN CH plus plus. So initially the value of sync is 0. Now it has become 1. Now when the process P2 executes, now sync value is 1. So when he is executing the wait operation, so 1 less than equal to 0 condition fails. Now P2 can access the critical section, then S minus minus. So again SYN CH value becomes 0. And now P2 is executing and the state S2. So I think you people might have understood now. So what is the statement we said? S2 can execute only when S1 has completed. Now with the help of this particular variable, semaphore variable, you are making sure that P1 executes first and then P2. It's very simple, isn't it? Isn't it? It's very, very simple what we have did here. Shall I explain it again? One more time I'll explain it. See here. So we have, let me write a wait operation first. Wait, capital S. Okay. So while S is less than equal to 0, this is the wait. S minus, S minus minus. And whereas coming to signal, capital S, simply S plus plus. Now here P1, what is saying? Here we are assuming that P1 is already allocated the critical section, means he has executed wait and he has been given the critical section. So what will be the value of sync since we are using a semaphore here SYNCH instead of a variable name S, you can use SYNCH or you can use S also, not a problem. So here the sync value is initially 0. Now when P2 started executing, he first calls wait operation. So here the S sync value is 0. So here you can see 0 less than equal to 0, condition true. So this particular process P2 should enter into a waiting state. Okay, until what time the P1 is giving signal. And once P1 has executed this statement, he will give a signal. Signal. So what is the statement we have signal? S. So sync we are giving. What is the value of sync we have? 0. So I'm giving it here 0. So S plus plus is nothing but S plus 1. So 0 plus 1 is equal to 1. Now the sync value becomes 1. Now when the particular process P2 executes after some time this wait operation, now what is the value of sync we have? 1. Now again check the condition. 1 less than equal to 0, condition fails. Then what we are doing? We will be allocating the critical section to this particular process P2. And then he will be performing S minus minus. That is nothing but synchronization minus minus. So 1 value becomes 0. Now if P3 comes and try to execute wait, so he will come to know that S is equal to 0, so we cannot allocate. This particular process will enter into a waiting queue. And then P2 will be executing the statement S2. So this is the way how at a time one process can execute the statement. So I hope it's very clear with this, how this particular semaphore has been used in order to solve your critical section problem. Okay. Now, next comes implementation. Well, how we can implement this particular thing? Till now we have seen what do you mean by semaphore? What are the statements we have with respect to you, means what are the operations we have with respect to your semaphores, and then what are the different types we have that we have discussed. In this part, we are going to implement it. Well, before implementing, I want to flash some light here. Well, even though you people are using this wait and signal operations, they are similar to your mutex clock concept, what we have discussed in the previous session. Means it is almost similar to it, almost 90 to 95% similar to your mutex clock. And we know that in mutex clock we have a problem. What is the problem we faced? Something called as busy waiting. That's what in the wait operation I'm writing as busy waiting. While condition busy wait. So we are entering into busy waiting. What do you mean the busy waiting? It will, that particular process which enters into a busy waiting, it will keep on after some time try to execute that wait operation. So if it finds that the critical section is busy, then it will wait for some time. Again, it will execute that wait operation. Means there is a spin is going on. That is what we call it as spin lock. It will keep on spinning until he will get the critical section. So in this, what did we say? What is the problem we face there? The CPU cycles are getting wasted there, isn't it? The CPU cycle means it is not giving a chance to another process which might require some other critical section. It is in the queue waiting for some other thing, but this particular process is not giving a chance because he is only after some time keep on rotating, executing it, again coming back, executing after some time, again coming back. So this rotation is actually killing the CPU cycles. So what happens here? So totally the cycles are getting wasted. To overcome that, we are going to remove this particular concept. We are going to modify this wait operation and signal operation. So what we will do is, whenever a process finds that a critical section is busy, he will not wait for some time and again execute that wait operation. Rather, this particular process will be blocked. And the blocked process will be placed in the waiting queue. This will be placed in your waiting queue. You're getting my point? Whenever a process executes to find out a wait operation, to find out whether critical section is available or not. In case if the critical section is not available, it will simply block himself rather than executing again. It will block himself and that particular process will be placed in the waiting queue. And the CPU scheduler will take another process and he will execute. He may require some other critical section or some other resource. So that particular process will be executing it. Now, since this particular process is blocked, when he will wake up, so he has to wake up now in order to execute. When this particular process will wake up, whenever, whichever the critical section this process is requesting, that is already with some other process P0. So whenever this particular process will call signal, then this particular process will be waked up and then this will be moved from a ready state. From a waiting state to a ready state. And now this particular process will be given a critical section for execution purpose. It's very clear. Very damn clear it is. Please understand the concept here. Whenever a process is requesting a critical section, if the critical section is not available, he will block himself and then we will place it in a waiting queue, P1. Okay, and this critical section is present with some process. So whenever this process will call signal operation, then this particular process will be will be waked up using a wake up function. Okay, and then this particular process will be given to your something called as that particular critical section to execute the operation. So what happens? He is not wasting the cycles. CPU cycles are not getting wasted. That is what exactly working on in this particular thing. I hope it's very clear in this particular concept. So two things we are going to add here: block, wake up. So using this, we are going to modify the wait operation and the signal operation. These two operations we are going to modify. Let's see how it is. See here. So we are going to busy waiting now. As I told you that there will be busy waiting. So because of this, we have a problem. That's whatever I've explained you. So that is what represented here. Now in this scenario, I am going to use a data item as I told you. So here we are going to modify the wait operation as I told you before. Same way we are going to modify signal operation. So definitely we require some data types, data items. So I am using two data items here, value. So this value is nothing but your semaphore value. That's why it is a type integer. And then we have another thing, something called as a pointer, which represents, since a process when it is blocking it, we are entering that particular process into a waiting queue. Na? So there will be multiple processes waiting for that particular critical section. So all these processes are actually getting stored in this queue. So we require a list to know that which is first, which is second, which is third, which is fourth. So for that, I'm using this particular pointer here. Okay. So the operations we are going to use block, as I told you, and wake up operation we are going to use in this particular scenario. Now this is the data structure I'm going to use. This is a simple C language structure. You people can easily understand. I have used the structures concept here in this particular case. Type def struct. So I'm using two values, data items, as I told you, int value. This is a semaphore value. You can assume like this, and struct process list. Okay, pointer list. Now this is the one which actually consists of all the list of processes which are in a blockable state. All that information is present in this particular thing. And finally, what kind of semaphore? Since I'm using a structure for semaphore, I'm representing like this. So let's see how your wait operation is getting modified. So earlier, okay, let me erase it up so that I can use this. Earlier, wait operation, let me write it up here. How we use that? So wait, basic one, S, Y, S is less than equal to 0, busy wait. So here we have a problem. Okay, this is similar to your something called as mutex law. Same way, signal S, S plus plus. Now see, there is a lot of difference now. Wait, semaphore, star, S. So this is common. This is the parameter. Wait of S. This is the parameter I use. But the only difference what I am doing here is I am doing S value minus minus. Okay, what I'm doing here, the semaphore here, we are checking the condition. Then we are, if the condition is not satisfied, then we are decrementing. Means the critical section is available, then we are decrementing it. But in this case, I'm initially decrementing it. I'm not bothered about the condition. I'm simply decrementing it. Okay. After decrementing means that critical section we are giving to that particular process. We are decrementing the value. Then I'm checking the condition whether it is less than 0 or not. There is a small difference here. Please see here. Here I have used something called as less than equal to 0. But here I am saying less than 0. There is a small difference. If the value is less than 0, that indicates that no resource is available. I am simply adding that particular process into a list. That is nothing but your waiting queue. I am adding that particular process into the waiting queue. And after that, I am blocking that particular process. Okay, that particular process will enter into a waiting queue and it will block himself. This is what we are doing. So here, why we are using this one, I think you might have understood. So this is the list what we are using. So to place that particular process in the list, we are using this pointer as list. Okay. What about signal now? Signal, earlier we had only a single statement, something called as S plus plus, right? Here it is. So S plus plus. But here we are, what we are doing, first we will increment the value plus plus plus, and if the value is less than or equal to 0, so if it is equal to 0 also, that indicates that there is a process, means there is a resource available or the critical section is available in this case. So remove a process from the S list, so remove a process from this, and we will wake it up. So we will wake that process so that that process can be allocated the critical section. So so what you are understanding by this particular two concepts here, that if the value of the semaphore is negative, then no resource is available. No resources are available. If it is equal to 0 or greater than 0, then resources are available. So we can directly allocate the resources to that particular process. That is what it's saying in this particular scenario. That is the only difference what we have. Now with the help of this, what happened? We are removing the main purpose to modify this particular code, and this particular code is only because of one reason, to remove that spin lock, or we basically call it as busy waiting. To remove that busy waiting, this one, we are actually modified this particular code, and this is much more better when compared to your previous one. Okay, so that is what is explaining in this particular thing. But okay, so this is the whole concept related to your semaphores. But since we are talking about semaphores, one by one doing and all, there is a small problem with respect to this particular thing, and that is what we call it as deadlock. Well, basically deadlock in depth we will be discussing in the next two, because this is the part 2 of your fourth unit, process synchronization. So deadlock and starvation. Okay. So here I'll just explain you how this deadlock situation is coming up. So deadlock, when it comes, when two processes, let us suppose we have two different, I'll explain with example. We have two processes P1 and P2. We have two semaphores here, two semaphores, S and Q. Okay. Let us suppose the process P1 is having a semaphore S. He has acquired that semaphore S, and after that P2 has acquired a semaphore. Immediately after that P2 has acquired semaphore Q. Now, after some time of execution, this particular process P1 requires Q to complete its execution. But this Q is with P2. Means he will wait. He has to wait until P2 is releasing Q. And whereas coming to P2, after some time of execution, he requires semaphore S, okay, to complete the P2 execution. But this semaphore is with P1. Now what happened here is, P1 will not release this semaphore S until he is getting this particular semaphore Q. And the same way, coming to the process P2, he will not be releasing process Q, semaphore Q until he is getting S. Now what will happen? This fellow will not release S until he is getting, until he is getting Q, and he is not going to release Q until he is getting S. So what happened finally? No one is going to release that particular semaphore. Now ultimately what happened? Till lifelong, until that system exists, these two processes will not be able to execute their statements. And that is what we call it as a deadlock situation. Deadlock. None of them will be able to execute here. Why? Because he is not willing to release this resource, and P2 is not willing to release this resource until he is getting the next one. So finally what will happen? Definitely there will be a deadlock. No one is releasing. So these two will not be able to execute this particular statements, or that they will not be able to complete their execution till that system exists, until that whatever the lab, it may be a laptop or a PC, until it becomes some 10 years, 20 years, till then this processes will be present there only like that without executing it. That is what we call it as a deadlock. So here he has given a statement with respect to a deadlock. Okay, let me show you a. So what is saying that two or more processes are waiting indefinitely for an event to take place, and that can be done with the waiting process. So here we have two processes and they are waiting for event to take place. So he is having S, Q. So Q, S, waiting. So they are waiting for this P1 is waiting for some event to take place. What is that? Release of Q by the process P2, and P2 is waiting for release of S by the process P1. They are waiting indefinitely, means infinite number time they are waiting for that, and that is what we call it as a deadlock state. Yeah, here is the example what I've explained it. So same thing whatever explained earlier, that is what been represented. Now another problem with respect to this particular semaphore is indefinite blocking of starvation. There might be a possibility that sometimes a particular process might be blocked depending upon the priority, so that will lead to a starvation. Okay, and this we already discussed. Starvation we have basically discussed in unit 2. I think you don't have to explain much more. So starvation is one of the problem with respect to your semaphore what we have. So that we will be try to overcome in monitors concept. Monitors will overcome this particular problem. That is nothing but your deadlock and starvation. Well, this is all related to your deadlock, semaphore concept, and we'll wind up this particular session here. So please go through this. This is one of the important topics with respect to your unit 4. Okay, and based on that only we will be discussing about monitors. If you understand this particular concept very well, we will be implementing this semaphores in your synchronization problems, which is the next session. In the next session, we'll be discussing about some problems and how we can implement this semaphores and try to overcome that problem. We will see it. And monitors will try to overcome the problems that we have with respect to semaphores. That is nothing but deadlock and starvation. So that we'll see in the next session. Thank you. Thank you for watching this video.